So below this, we'll add that create model. Obviously, it's going to receive that file name that we were passing in the SkinEffects. So the first thing it does is it creates a new skin model, passing in the GPU and the SkinEffects. And we can pass to that model, we can pass to it the debug texture and the use debug texture. So the model is only really holding a reference to it. It's the loader that actually keeps the debug texture. There'll be 6 main important parts to the create model. Got our create root node. This prepares to build the model's tree. To do that, it will need the root node. Then we're going to create the meshes and bones for the model, and then set up materials and textures for each mesh. Then we'll create our tree transforms, passing in the model, the root node of the tree, and the scene's root node, that's the Assimp scene. As it says here, we recursively search and add the nodes for our model from scene. This includes adding to the flat bone list and the node lists. We'll go into more detail on this later. We're going to also use something called prepare animation data, and that sets up each of our nodes animations frame list. So all the keyframes for each one. Copy vertex index data, that copies the vertices and indices for the meshes. And you may remember that info is that load debug info that we made earlier, and we can say .assimp scene dump. So depending on whether we have the boolean turned on for that at the top in our debug, this assimp info, that'll determine whether it actually dumps it. Otherwise, it'll just return. And we also call the display info, passing in the model and the file name. And again, depending on which booleans are turned on, it'll display information about what's in the file, as well as information that's been stored in our model. By this point, the model's been fully created, and we can return that model. So we'll go over this process sequentially. We'll start with the create root node, and we'll put that right under here. And now down here, we have this create root node. We passed in the new model we created, which we still have details to fill for, and we passed in the Assimp scene that we loaded. So we'll allocate our model node for our root node of the tree, and we'll set its name to be the scene root node name. So first we got to set that initial local matrix transformation for the root node by assigning it to the value of the root node's transform in the scene, except we have to use this extension toMg transposed to make a monogame compatible version. Since this is the root node, it doesn't have a parent, and we're going to be using the combined matrices. We'll just assign the combined matrix for this to be the local matrix. So that'll be that initial local offset and orientation for the root node. If our material information boolean is turned on, that optional debug that we have, then we can use this info.creatingRootInfo with this message here, which will show the root node name and the number of children and the mesh count, and if matrix info is turned on, it'll also show that root node's transformation matrix in the form that we're going to use. We don't yet have a matrix 4x4.2 monogame transposed extension yet, so we're going to add that toMg transposed extension in our skin models, skin mode helpers folder. We have that loader extensions. We'll go in there and we'll add that to our loader extensions. So I'll do that above our additional info extensions. This will be used more frequently. We now have a bunch of extensions that I added. I'll just kind of go over these quickly. The main one that we need right now is this test value. Well, that actually isn't really an extension. This test value here is just a method that's used by our extension down here, and just makes sure that we have a valid value inside our matrix for each entry. So if float is not a number or float is infinity, this cannot be used, and therefore we're just going to return 0. Otherwise we can just return the value. And here we're attempting to make it inlined, so it's not actually calling the method, which slows it down a tiny bit. In this case, because it's in a loader, it's not going to be that critical anyway, but in this case we have a Boolean version that is called isFinite, and that's essentially all it's doing is checking and returning false or true based on whether it is finite or is infinite. In this case, it's the same thing applied to a vector, and we're using this isFinite up here on each of the entries. If any of those happen to be false, then it will return false. If they're all true, then it is a finite vector. In this test vec, it's kind of the same as this test val up here, except we're applying it to a vector and setting each entry to 0 if it's trying to misbehave. Okay, we got this, which converts to monogame, returning a monogame matrix, and applying that to a matrix 4x4. So this is an extension of the matrix 4x4 .toMg. So M11 to 14 is assigned to MA A1 to A4, and we do the same thing for 21 to 24 and B1 to B4, so we're just assigning those entries appropriately. This toMg transposed is doing exactly the same thing here, except we transpose the matrix before we return that matrix. And down here we got a 3x3 matrix version, in case we need to do that with a 3x3, and we want to return it as our 4x4 monogame matrix. First of all, we transpose the Assimp matrix, make the appropriate assignments, this time going 11 to 13, 21 to 23, that sort of thing, and A1 to A3. But you'll notice on the end here, I got the m.m14 equals 0, 24 is 0, 34 is 0, and then 41 to 44, they're all 0, except 44 is actually a 1, so that W entry is a 1, which we need for that matrix to work correctly. Now let's go back to our SkinModelLoader, and now we can see that this is now satisfied. Now that we've set up our matrix for our root node of the tree, we come back to here. The next thing on the list is we got to create meshes and bones. So we may as well add that immediately after the create root node. We'll keep things in order. So for create meshes and bones, we got our optional debug info, and for our model, meshes will become a new array of skin meshes based on how many meshes are in the scene. So we'll loop through the scene meshes and set those up. We'll use Assimp mesh to refer to each of those meshes. Then we'll start by creating a new skin mesh to add using our skin model skin mesh type. We'll copy over the name. We'll provide the current index as mesh number. Just for the moment, we'll say the texture name is default. We can copy over the material index, and we can also use that index to find the material inside the scene's material list and get its name, and just copy over that name into material name. And these meshes may also have a bones list, so we'll get a reference to that. First, let's copy over whether or not it has bones. We'll create a new flat list of shader matrices. Those are bone matrices, and we'll use the Assimp mesh bones count plus 1. This way, for this mesh, there can be a matrix transformation for each bone that's associated with this mesh. There might not be a bone or node animation. Let's make sure that shader matrix 0 is set to matrix identity. So even if the bone count is 0, we've got this plus 1 here to make sure that we can at least have this 0 here, and we keep it static for the entire duration. Similarly, we can allocate the same number of bones, skin model bones here. So this mesh will have a list of mesh bones that will be a new type of this. Next, we got our dummy bone. Can't link this to the node. That must wait. It's not created and only exists in the model, not in the Assimp bone list. So we're creating a new model bone here, 0, setting the offset matrix to identity, providing the mesh name and mesh index. Bone index is 0, and then we're just going to refer to that with this flat bone and use it down here. Now, using the Assimp data, we'll create an add bones. And we're going to loop through our Assimp mesh bones based on the Assimp mesh bones count. As you may recall, we just set up our Assimp mesh bones up here to refer to our Assimp mesh bones, and Assimp mesh refers to our current scene mesh that we're looking at. So we're just going through the current scene mesh's bones, essentially. And henceforth, Assimp bone will refer to the current bone we're examining. I'm not sure why this line is here, Assimp bone name equals, because I think this is shorter anyway. We're just going to go AssimpBone.name. So I think I'll just delete this line. I don't think that's being used. And we already added a dummy bone here for 0. So we're going to say that our current bone index is going to be ABI plus 1. We can start by initializing this mesh's shader matrix for the current bone to be the identity matrix. And for this mesh bones list, for this model bone, we'll create a new skin model bone. And we'll set flat bone to refer to that current bone, the model bone that we just created. Actually, you know what we could have done up here? We could have used this reference here and then just shorten all this to be flat bone. Not totally necessary, but we did it anyway. Okay, so we've created our new model bone and we're referencing it with flat bone, and we'll copy over the name from the Assimp bone as well as the offset matrix. We're using toMg transposed to make it compatible. We'll copy in the current mesh index and also the current bone index. And the vertex weight count for this bone. And it looks like I got some redundant code here. Probably don't need this here. This is already referring to this, so that should be addressing the same memory already. So that wraps up the skin mesh's model bones, and now we can add that new skin mesh to our model's skin mesh list at the current mesh index. And if we wanted mesh bone creation information, we can use our debug to show some extra information. That's in that load debug info we made earlier. Okay, and that should be it for create meshes and bones. The next thing on our list is set up materials and textures. Okay, so set up materials and textures. We'll put that down below again under the create meshes and bones. Takes our model, the Assimp scene, and the current mesh index of which we'd like to load materials and textures. Wait a minute, why are we taking in the mesh index? This should do it for the whole model. We don't need the mesh index. Okay, so that was probably just an error. Before we start loading those textures, let's store the current setting for our contents root directory. And that way we can restore it after we're done at the bottom down here. We'll first loop through the Assimp scene's meshes. We'll get smesh as a reference to the mesh we're dealing with at the moment. We'll set our material index to be the scene mesh material index. And then we'll have this Assimp material refer to that material so we don't have to use all this. Then we'll copy the material colors and properties from the Assimp material into the ones for our own mesh. We don't yet have an extension though for the Assimp colors to convert them to monogame color. So let's just go over to our skin model helpers over here and go into loader extensions, and we'll add those in there. I'm going to go under our toMonogame transposed and before the additional info extensions, and I'm just going to add one here, and this will return a vector 4 from an Assimp color 4D. So we're just putting the red, green, blue, and alpha components into that vector 4 and returning it. Now let's go back to our skin model loader, and these are no longer underlined. So we've got ambient, diffuse, specular, emissive, opacity, reflectivity, shininess, sort of the amplitude of how much light is shining off of it, and we got the shininess strength, which is like the glossiness or the specular power. It can be used to narrow and intensify highlights for a more wet or metallic looking effect. Our bump scaling, which we could use, I'm not sure if we're going to, but we could use it as a multiplier factor to be passed to our shader to amplify or diminish the effects of our normal mapping. Is two-sided, could be useful for glass or ice. Stuff like that would have to be rendered separately so that you kind of have that painter's algorithm so that pixels aren't being rejected based on depth and you can still actually see through it. Got this little mini region here with ones that you might want to add in the future that I'm not actually currently using, so I just turn them off for now. But we got reflective property, transparency property, or a transparency factor. We're already using opacity up here. PBR material, that's physically based rendering, so it just depends on what you're using. I'll collapse this. We're going to say Assimp material textures is equal to Assimp materials get all material textures. And if you look here, that is an array, texture slot array, obviously, because that's what this returns. If material info is requested, we can output to the console display the mesh name, material index name, the material index showing here, indicating that we're getting the material textures. And we will loop through the texture slots here. If you're curious about texture type, there's this sort of comment here. 0 is none, diffuse is 1, specular 2, ambient 3, emissive 4, height 5, normal 6, shininess 7, opacity 8, displacement 9, light map 10, ambient occlusion 17, reflection 11, base color 12 for PBR, normal camera 13, which is for PBR normal map workflow. Emissive is 14, PBR emissive. Metalness 15, PBR shininess. Roughness 16, again that's with PBR. I don't plan on using PBR yet, although it does interest me a lot. So I'm just going to collapse this, but that's there if you're interested. Here we're going to get a texture index, texture operation, and our texture type, in this case as a string, the file path, and we got this get file name. We don't have that yet. So let's just bookmark this and go down and create a get file name, and then we'll come back to this part. Down at the very bottom underneath, we've got this new region here, helper methods, and any little helper methods we'll just add into here. And we're going to use this elsewhere, so let's make sure this is public. We set use both separators true when we pass that in, and we pass in our string. So we're going to split up the string of the file name or file path from the original scene for what the texture path is, and split it where that .png is or .jpeg or whatever it is. And by default, we'll assign f to be 0, being the first string in that list. If there are 2 or more strings, it should be the png, or whatever the extension is, would be the length minus 1. So we want length minus 2 to get the one before that. And that should be the file name without the extension, although there's still probably path attached to the front of it, so we gotta split that up as well. And we said this is true, so if it sees a / or a \, then we're going to split it up based on either of those 2 characters into an array of strings. Otherwise, we're only going to split it up based on when we see that / character. At this point, we know that the string we're looking for is going to be the last one in that array, which is length minus 1. So basically we're returning the file without the extension and without all the path information. So now we can pop back up to our setup materials and textures, and this part right here, get file name, we'll get from this file path here and give us the texture that we're looking for. We can take it from our content folder. We'll use this path.combine app domain, current domain base directory with content root directory, and using that file name that we just got, we'll add on a .xnb and we'll check to see if it exists using this file exists equals file.exists and that full file path we just made. And that should work. If it doesn't, if it's false, we can try it using that file path name without extension that we created earlier in our load and see if that one is found. If true, we'll set content root directory equal to path.combine content with that file path name without extension. If we still couldn't find it, we'll try the alternative directory that was passed in and combine that for our path. And if it exists, is true, then we'll set content root directory, combine content with alt directory. Actually, chances are good in our case, we're going to pass in that alt directory as the kid folder and use that. So it'll be in content/kid/. Okay, I'm going to go down a bit. If we want to know material info, we can output that here. Just scroll to the right here so you can see what's here. Material index, texture index being shown, Assimp material textures length, how many textures there are, showing index, texture index, the type, the operation, the name, whether or not it exists, and the file path. Now let's move on to loading those actual textures. First, if it's a type diffuse, we'll assign our texture name for our diffuse texture to the current file name. If we were able to find the file in one of our content folders, we'll say model mesh's mesh index texture diffuse is equal to, and then we'll load content.load that file as a texture 2D. And we can print out any extra information about the current status of what we're doing on the right here. And for type normals, this time it's going to be text norm map name is equal to that. And we'll say .text norm map is equal to, and then load it. And then show the current status over here if material info is true. You'll notice too, for each one of these, I have this else console right, so we can provide a warning to the programmer that the file is not loaded. And we got one for height here using text height map name. Text height map, got one for reflection map name, text reflection map. I noticed I did not include anything for specular, and I actually do plan on adding specular, so I'm just going to add that. Actually, I think I'll copy normals and put it in between normals and height and change it to specular. So let's change this, specular, and I'll change these messages over here in a second. I'll probably pause it and do that. And we got to make sure to change this text normal map to text specular. Oops, we want to change this one first. It's text specular name. If I have that, I might have to add that. If I peek skin mesh, I can see that I actually don't have text specular name in here. May as well add that. Okay, we got that, and specular is already in here. Now I should be able to go text specular name, and then this one, text specular. There. Now I'll just adjust this to say specular. Okay, so I changed these to specular to avoid confusion. And by now we should have loaded the textures we need, or at least for now, and we can return our content root directory to the one that we saved, and then we can return. We modified this because we don't need to pass in a mesh index, because we're doing it for all of them. Now we can work on create tree transforms. Recursively search and add the nodes for our model from scene. This includes adding to the flat bone and node lists. Alright, so let's go down below our materials and texture setup and create tree transforms. Alright, so I added this tree transforms region now. And I've got this kind of confusing brief summary here. Recursively get the scene node stuff into our model node. So that's basically what this is doing. We're going to get the node name, init the local matrix, assign bone, non-bone mesh transforms to corresponding mesh. We're going to match up by name, mesh and index, bone index with the current node. So each mesh has its own offset matrices for each of the bones in that mesh's bone list. Well, we'll examine that a little bit more in a second here. And we're going to create the children. So we're taking in our model, we're recursively taking in a model node. Above, you've seen that we start with the root nodes, that we can go through this tree recursively. Take in the current Assimp node, and there's a tab level for console display. So in the first loop of this, we'll basically be assigning the root node name to the root node name in our model. We'll copy over the current node's transform, and we'll get the monocane compatible version by going to mg transposed. That's that initial transform for the binding pose. If this node is a mesh instead of a bone, it says here, has meshes, then we'll set it as isMeshNode is true. And then we'll go through the list of mesh indices, and using that mesh index, we'll reference the corresponding mesh, and then assign the node with animtrans to be the model node that we passed in up here. So that tells the mesh to get its transform from the current node in the tree. The next thing we're going to do is we're going to loop through our scene's meshes. And for the current model node that we're looking at, so each one of these skin meshes here has its own bones list. So using the model node, or the bone from the regular bones list of the skin model, we'll use the name to find the corresponding bone in the unique bones list that associates with this particular mesh. The thing to keep in mind is that each mesh is going to have its own list of bones because they can have their own offsets and such. So we're going to need that bone, and we're going to need the index within the mesh for that bone. We don't yet have a get bone for mesh, so we'll just bookmark this spot here and we'll go make that get bone for mesh, and we'll come back here later. So let's scroll down to our helper methods section, and after get file name, we'll add the method we need. Okay, so now under get file name, we have this get bone for mesh, taking in the current mesh from our skin mesh list, the name we're looking for to match it up, and we're going to output a reference to the bone that belongs to the list of bones for this particular mesh, as well as the index to it. So we'll initialize found as false, bone is null, bone index in mesh is 0, and then we'll loop through this particular skin mesh's unique bones list, the mesh bones list here, and find the corresponding name that matches. We'll set the index to be the current index, and we'll reference the bone that we found that matches. And we'll say found equals true. And when we're done, we'll say return found, whether it's true or false. I suppose at this point, though, we could just say return true or use break. Okay, let's go back up to our bookmarked location. So now on this line here, get bone for mesh, we should now have a reference to that bone and the corresponding index. Set our model node has real bone to be true, is bone on route to be true. We'll assign the bone that we found to have a mesh index as the current scene mesh index in this loop. And we'll assign the bone index of that matching bone we found to use the bone index in the mesh, which is that corresponding index inside our list of bones that belongs to the current mesh. Then for the current model node, we can add to our unique mesh bones list this model bone, which has our mesh index and the bone index. I mean, there could be only one of these, but there could be 3 of them. It just depends on how many meshes this bone is influencing. If we turn on our node tree info boolean, we can show the node tree information using our load debug info. Scroll down. Finally, we're going to loop through the children, the current Assimp node. We're going to make Assimp child node refer to the current child in the Assimp node's children. And we're going to make child node here refer to a new skin model node that we will add. We'll set our new child node's parent to be the model node that we passed in up here. We'll set its name by copying from one of the child names, by copying from the current child name in the Assimp children that we're looping through. If the parent is a bone-on route, then we'll say the child node is bone-on route is true, part of the actual tree. Now we can add that new child node that we made into the children list for the current model node. Then we'll recursively call create transforms, that's this method here, passing in the model again, the current child of each, and the tab level will add 1. That's just for the debug info. So essentially we're just setting up our initial transforms and linking together our mesh index and bone index information. Going back up to our create model again, the next thing we need to create is this prepare animations data. So let's go down below that one that we just made and start with that one. Now under our create transforms, we got this new section, prepare animations data. Gets the Assimp animations into our model. In the source code, there's these 3 links in here, so if you want to check that out, we're going to take in the model and the Assimp scene, and we're going to loop through the scene's animations. And we'll reference the current Assimp animation with this Assimp anim, and we'll start by creating a new instance of a rig animation called model anim. And we'll just copy over the animation name, the ticks per second, the duration in ticks. We'll calculate the duration in seconds as being the duration in ticks divided by the ticks per second. And the duration in seconds added we're going to set to be equal to the added looping duration. You may remember that's an optional public member which we can modify elsewhere for adding extra padding to our animated loop. Or we can set default options and pass it in that way. Now we've got this total frames here set to duration in seconds times ticks per second. And I have it commented as just a default. I don't recall using total frames anywhere. I don't think we're actually using that for anything. So you might want to double check that, but that might be something we could probably even remove. I think for now I'm just going to comment this and go to the original here and comment it as well because I don't remember using that. So yeah, I'm going to comment this out too, and if I was wrong I'll come back and uncomment them. We got our booleans that we copy over for has node animations, has mesh animations, and for each of our rig animations, or model anim in this case, we're going to have a list of animated nodes that contains our scale, rotation, and translation keyframes for the nodes. Essentially a list of these guys right here. We'll scroll down a bit and we'll loop through the animation channels. We'll use this anode anim lists to refer to the current animation channel, and node anim will be a new anim nodes, and again that's this keyframe stuff. We'll copy the animation name as node name. The next thing you might see here is the model node ref is equal to get reference to node, passing in the current animation name or node name and the model node for the root of the tree. We don't have this yet, so let's go create that right away so we can understand what's going on here. We'll go down to our helper section again, and below get bone for mesh we'll add a new one. So that animation node, we're going to use that name and search for the matching model node, otherwise we return null. Starting with the current node, we check to see if the name matches the name we passed in, and if it does, we can return this node. If the current result is null and there are children, then we'll loop through those children and we'll say result is equal to get ref to node. So we're doing this recursively. It's partly why we have to have this here. Get ref to node, passing in the name and the child, the current child in this loop. If the result is not equal to null, we return the result because we found it. And finally, at the end of all this, we're going to return the result. So now back up in our prepare animations data, we can go back to that line where we had model node ref is equal to get ref to node. Now we have the corresponding model node for this animation. If we didn't find it, though, we'll output this warning message, should not be null. So we can assign to our node anim dot node ref equals that model node ref. We'll go down a bit. Now we get the rotation, scale, and position keys for each key list in an anode anim lists dot rotation keys. In this case, key list is going to be an Assimp quaternion key. OAQ, the current quaternion, is going to be equal to that key list value. So get the open Assimp quaternion. That's what OAQ stands for. And we can add to the current node animation the quaternion rotation time, qrot time, and we add to it the value that would result from keylist time divided by Assimp anim ticks per second. And then we want to add the actual quaternion rotation value into our node animation. To add that though, we're using this open Assimp quaternion.toMg, so we have to add that extension into our skin model helper's loader extension. So let's go into that. So maybe up above here, just after this aggressive inlining stuff, right before the matrix conversions, okay, I've added this extension for the Assimp quaternion, which is going to return our monogame style quaternion. We can say AQ, which is that quaternion we passed in, that Assimp quaternion, dot get matrix, which returns a 3x3 matrix into M. And then we can say N is equal to that matrix to monogame transposed, which we already built down here. Then we can create our quaternion from that matrix as a monogame quaternion and return that quaternion. So let's save and go back to the skin model loader. Actually, if we go back into the skin model loader, you see right under where we did this, you can see that we're going to need to add another extension here to monogame for the Assimp vector 3D. So let's go back in there again and add that. This time I think we'll go down to the bottom where we have this vector 4 conversion. Maybe just before that. Okay, so I now added this, which is going to return a vector 3 and receive an Assimp vector 3D. Essentially all we're doing is creating a new vector 3 and assigning the corresponding values. We'll save and go back. So again, we're going through each of the position keys. We're getting the converted value for that position converted to a vector 3, and we're using the same sort of calculation to get the position time for that keyframe. And we're adding to our position list the current position. We'll go through the scales as well and add keyframe time values and scale values. Now we can add this node anim to our list of animated nodes. After we're done looping through the channels, we can add our model anim to our list of animations in our model. And that should conclude the preparation for animations data. So now let's go back up, and the next thing we need to work on is to copy vertex index data. The last thing we need to do before we can return our skin model is copy the vertex and index data for the meshes. As usual, we'll go down and add that below under Prepare Animations Data this time. I added this copy vertex index data, taking the model and the Assimp scene and the mesh index. Actually, we don't need this mesh index thing here. We're going to loop through all of them. If you want to learn more about the mesh structures, you can use this link here as a guide. So looping through these scene meshes, let's get a reference to the current mesh. If we want to display information to the console for debugging, we can show mesh info using the mesh and mesh index. We'll also loop through the UV components, getting the value for the current UV component count, and display that UV component count. And we'll say, next up, we're going to be copying indices. We'll make an array of indices, which will be equal to the number of triangles times 3, because we need 3 indices per triangle. And we'll loop through those triangles, mesh.faces.count, and we'll say that the current face is equal to mesh.faces of that index. We're expecting all of them to be 3 because it's been triangulated. If index count is not equal to 3, we'll put out a warning message about that. We'll loop through our indices and set ind to equal the current index, and we'll copy that index into our new index list, this array that we made here, at the current number of indices, and then we'll increment num indices. So we've copied our indices. Let's do the vertices next. We'll first get the number of vertices from mesh.vertices.count. Using our vertex declaration type that we made, vertex norm map skin, we'll have an array of those as v, and we'll allocate that for the number of vertices. We'll loop through our vertices, saying f is equal to the current vertex, and we'll add that vertex to our vertex list as the vertex.position. Next, we'll do our normals. We'll loop through the mesh normals, get the current normal, and copy that normal in. Actually, we probably could have just put all this up into this loop up here, since they should be the same amount. Optionally, there's this section here with vertex colors. I have the define for this disabled at the very top here, where I commented this out. So if we turn that on, that code becomes active. Right now it's turned off because we're not going to use it, at least not right now. If it was on though, we would assign C to be equal to the current mesh's list of vertex colors, mesh.vertexColors channels, MI, so that's for the current mesh. We'll say hasColors is false. If mesh.hasVertexColors for this mesh, MI, we'll say hasColors equals true. We'll loop through the vertices based on the vertex count. And if hasColors was false, then we'll just set each vertex color to white or 100% for every channel. Otherwise, we'll copy into the current vertex color, new vector 4, and from that C up here, which is our list of vertex colors, at index K, the red, and we'll do the green, blue, and alpha channel. Next, we'll get our UV channels. Those are vector 3D from our current mesh. And we'll loop through that based on the length. And for the current channel, we'll get that list of UV coordinates into vertex UV chords. And then we'll loop through the texture coordinates based on that UV coordinates count. As an Assimp vector 3D, we'll get the current UV is equal to the current vertex UV coordinate in that loop. And then for our vertex, we'll say vertex of the current UV count is equal to a new vector 2, and we'll get the X and Y components of that UV that we got here. And then we'll increment our UV count. So now we got our UVs. Let's go down to tangents and bitangents, which, as you know by now, is used with our normal mapping. So before, it seemed like I was having a problem with the tangents or bitangents being wrong. I'm not sure if maybe I was converting them incorrectly or something, but if we just copy them straight over normally, it didn't seem to give me the correct results. I might need a toMg extension or something for this. But if we wanted to copy them directly over, and oh yeah, keep in mind that we have to have this set so that the tangents exist or are generated during the load. As you may remember up here in the load, there is a flag right here, calculate tangent space. We might even be able to turn that off right now since we're not really using it. I'll leave it on just in case you decide to try going back to it. Let's go back down. So I'm just looping through mesh.tangents.count, getting the current tangent and assigning our tangent to be basically just directly copying it into a vector 3 into our vertex. And I did the exact same thing with the bitangent. So this might be incorrect. This coordinate system might be a bit different. So if you want to copy them, there's that option. You might have to do some kind of conversion. To be safe, I decided to regenerate the tangents, and we're generating the bitangents on the card. But actually, I think I might be doing it here too, which might not be necessary. So I'm pretty sure the following code is based off the normal mapping calculations used in monogame. And I'm thinking it's practically copied, just a little bit modified. So it starts off by allocating tan1 and a tan2, our vector 3s for the number of vertices we have. And we loop through our indices, going index plus equals 3 because we're going to get 3 indices. So we're getting the 3 indices per face. Technically, we're looping through the faces. We also get UV coordinate 1, UV coordinate 2, UV coordinate 3. We're just saying W1, W2, W3. We'll get the 2 U distances and the 2 V distances. So I think I have actually looked at how this math works before. I don't recall offhand exactly what's going on. But if you want to look into that, there's all kinds of resources on the internet on how to calculate the tangent and bitangent. So I'll just kind of briefly run over what code is in here and what it looks like it's doing. Looks like we're going the U1 distance times the V2 distance minus the U2 distance times the V1 distance, and we're setting that as the denominator. And we'll make sure that that value is something we can use in our calculation. We don't want to divide by zero error or something that's ridiculous. Let's change this to loader extensions. We don't have a loaders extensions. So we'll make sure that this is a finite number. Using the indices that we gathered up here, we'll select those 3 vertices, V1 to V3. And sort of like we did with the UVs, we'll get that horizontal distance between the vertex 2 and vertex 1, as well as vertex 3 and vertex 1. And we'll do that for the Y and the Z. So we'll create a new ester and teeter set of vector 3s. This one corresponding to the u, this one corresponding to the v. We'll say that the x is equal to that v distance, v2 distance, times the x1 distance minus the t1 distance, in other words the v1 distance, times the x2 distance. Anyway, I'll just let you go ahead and copy what's here. No point in saying what's going on exactly for all of these. In this one, instead of the t2s being here, this is going to be s1s. Instead of x1, y1, z1, it'll be x2, y2, z2. This one's going to be changed from t1 to s2 here, and then we go x2 to z2 here, and then x1 to z1 here. Each one of those is times by r, which is that factor we calculated up here. Now we can say tangent 1 for index 1 plus equals ester, and we'll do that for tangent 1 index 2 and index 3. And for tangent 2 of those 3 indexes, we're going to use teeter. It'll keep looping through those faces, because we're going index plus equals 3, until it's done all that, and then we can come down here and work with the vertices. And I'm sure you must have realized too that there are going to be repeats of certain indices, so that's why we're using this plus equals. At this point, we have all of the vectors accumulated, but we need to average them out. So we loop through all the final vertices and do a Gram-Schmidt orthonormalize, and make sure they're all unit length. So we'll loop through those vertices. We'll say n is equal to the current vertex normal. We'll say that t is equal to tan1 indexed by I from here. And if t.length squared is less than epsilon, in that case we couldn't find a good tangent for that vertex. Rather than set it to 0, which could produce errors in other parts of the pipeline, we just create a guess at something that may look okay. I think these comments were actually not mine, but originally from the monogame version that I copied this from. So to kind of get something that might look okay, we're going to go t is equal to vector 3 cross product between normal and vector 3 unit x, a unit direction on that axis. And if that one doesn't work out, we'll try t equals vector 3 dot cross with n and vector 3 on a unit y, so a unit vector on the y-axis. So hopefully now we have something that's okay. We'll say the current vector's tangent will be equal to the normalized t that we got here. And we'll say the bitangent is the cross product between the normal and the tangent. And continue. Since we're calculating the bitangent on the card, we might actually be getting rid of the bitangent stuff. So I might come back and comment some of the bitangent stuff out if I remove it from the vertex declaration. At this point, we'll continue because we already got our tangent and bitangent, so it'll go back to the beginning of that loop. Now, if everything was okay though, what we'd normally do is we'd say tangent is equal to t minus the normal multiplied by the dot product of n and t. And then we normalize that tangent using vector 3.normalize tangent. And we can store that in our vertex. Here we're calculating the handedness by saying w is equal to, and then saying vector 3 dot, getting a dot product between the result of the cross product of n and t and tan2 at the current index. And if that is less than 0, then we'll say the handedness will be -1, otherwise it's going to be +1. So that'll effectively flip the direction of our bitangent by multiplying it by +1 or -1. So we'll say bitangent is equal to cross product between the normal and the tangent times our handedness to get the bitangent to point the right direction. And then we can store our bitangent in our vertex. We'll go down a bit here and we'll get the bounding box now. This one's pretty simple. We're just going through all of the vertices. If an x position is less than the min x position, we'll set the new min x position to be that position. We do that for the y and the z, and then we use greater than to find the max ones, doing the same sort of thing. For finding the center, we're just adding up all the positions, and when we get to the end, we can say that the mid is equal to that value divided by the number of vertices here. And then we can also assign the min and max value that we figured out. So now we have a bounding box for the current mesh. After that, we're going to set up our blend weights and blend indices. We'll loop through the vertices, and we'll initialize our blend indices and weights to be vector 4.0. So next, we're going to restructure our vertex data for our shader. We'll iterate the mesh's bone offsets, set the bone IDs and weights to the vertices. So it'll also entail correlating the mesh local bone index names to the flat bone list. we're going to create an array of temp vert weight indices, and that'll contain that information we just mentioned here. We're going to need that for the number of vertices we have. We don't have this structure yet, so let's go to the very bottom and add it down there under our helpers section. Now at the very bottom of our helpers, I added this class, temp vert weight indices, got the number of bones for this vertex, the ID from our flat bone list, and we got our list of vertex indices and our list of vertex bone weights. So let's go find out how we're going to use these. We'll go back up, and so now our verts is going to have all this kind of data. If our current mesh has bones, we can proceed into here. So for the current mesh, we know it has bones, so we should make sure to record the mesh has bones. We'll record whether or not it has mesh animation attachments. Assimp bones will essentially be that list of bones for that Assimp mesh that we're referring to. So then we can output information about the bone count for that Assimp mesh and loop through those bones in that mesh based on that count. Then we'll refer to this current Assimp bone, and we'll get the name of it, and we'll set our model bone index to be the current index plus 1 because we got that dummy bone at the start in 0. If we have console info turned on, we can see some debug information. We got the mesh name, the bone name, the Assimp mesh bone index, and the weight count. And if there are vertex weights, we'll add on this information, the vertex ID of vertex weight 0. We're going to loop through our weights based on the vertex weight count of the current Assimp bone, and we'll get the vertex index using its vertex weights, using that weight index that we're looping through, and vertex ID. We'll assign that here, and we'll do the same thing for weight. If our current temporary vert weight data here is null, which it probably would be, we'll create a new one of those. We'll store the vertex index here, that's that vert ID we got up here, and we'll store our model bone index, that's this index we got here, as well as the weight, which acts as the influence percent for this bone. And we'll increment the number of bones for this vertex so far, until we're done adding all the weights for this bone, or I should say for this temporary vertex. So down here, in the case that we didn't have any bones, if there's no bone data, we will set it to bone 0 as a precaution. In this case, the verts need to have weights, and we'll set that to be bone 0, which is an identity matrix. This allows us to draw a boneless mesh, as if the entire mesh were attached to a single identity world bone. If there's an actual world mesh node, we can combine the animated transform and set it to that bone as well. So this will work for boneless node mesh transforms, which Assimp doesn't mark as an actual mesh transform when it is. So let's loop through these verts, create a new temp. We'll assign VE to be equal to that at the current index. And if its indices count to 0, we can go ahead. For indices, we'll add in this current index. For the bone ID, we'll give it ID of 0, which should be identity. And then for vertex bone weights, we'll give it a weight of 1. Okay, let's go down a bit. We got this note here, need up to 4 bone influences per vertex. Empties are 0, weight 0. We can add non-zero entries, 0, 1, 2, 3, based on how many were stored. Note, the bone weight data aligns with offset matrices bone names. Okay, so those correspond. We'll loop through the vertices. If the vertex, those are those temp ones we made. If it's not null, we'll refer to the one we're looking at as VE. So array index is going to be an array of the indices in VE, vertex entry. This array bone ID is going to be array of the bone IDs in there, and the array weight is the same sort of idea. So if there are more than 3 bone IDs, meaning 4 entries, entry 4 is technically index 3 here. So we'll go our vertex for array index 3 out of our array index list here. We'll set its blended indices .w component, which is the 4th index, to be equal to that 4th bone ID. And for that same vertex, for the weights 4th component, w, we'll get the 4th weight. And if there are more than 2, then we can work on entry 3. So for entry 3 here, using array index 2, that's the 3rd entry, we can say blend indices.z, which is the 3rd component, is equal to bone ID 2, which is the 3rd one, and we'll do the same thing for weights. If there are more than 1 in here, we do the exact same thing, substituting 1 and 1 here, and we're using y. because that's the second one. If they're more than 0, we can use the first entry, which is 0, in X, which is the first one, for bone ID 0, array weight 0. So each one of these bone ID, that's out of the flat bones list, in other words, our shader matrices, and it'll know which one to use. And then the weights, we're just assigning the correct weights to the correct vertex. Moving down, finally we can say model.meshes for the current mesh vertices, that list of our custom vertices that we made, is equal to V, because we finished updating our vertices. And we can say that the indices are equal to our indices list. And those were simply copied at the top here. If reverse vertex winding is true, so if we did want to reverse it, which I don't think we're doing, then we can loop through our faces by going through our indices with the index plus equal to 3. I would expect this should actually be, okay, yeah, I see that 0, 2, and 1 are switched here. I mean, we could even take this reverse vertex winding out if we don't ever plan to use it. Let's just flipping this 2 and this 1 around so the vertices wind in the other direction. Alright, so that's it for the copy region index data. It's quite a big one. I'm going to fold up these regions now and see what's next, because I think the skin model loader is actually done, and it's more so now just a matter of creating some example code. Now we have our 3 classes over on the right here. So in game 1, under the models and characters section, we may as well go and add those 3. We may need to right click on each one of these and provide the using for it. I made an array of skin model for hero animations. For now, I'm going to keep the characters animations in separate FBX files. It's a little bit redundant because the same skin mesh information and texture information is in each file. For now, I'm just going to do it this way, but later on, for efficiency reasons, I'll make a version of skin model, and in each version I can load the initial skin mesh character and the initial animation. Key difference will be that we'll have it set up so that we can have different clips of animation that have start times and end times in our model. Each one of those can be run independently and they can be interpolated together. And it would also be possible to use each one separately as a different instance with a different world position for the character. And so each one would obviously have its own current frame, which clip it's using, the start time and end time for the current clip. You could use Motion Mixer or whatever it is that you use in your 3D software, and you can mix all your animations together onto one timeline. Each animation has its own start time and end time, so depending on what clip you submit and which instance, it'll select the corresponding instance and corresponding clip to run. The skin mesh instance though, and the texture instance, all that stuff is just going to be the same. They're all just going to be borrowing from that. I suppose in the load you could add extra parameters to set up all the different animations, like an extra parameter list. Probably a better way to do it though, I would suggest, would be just to load everything normally so that you got the full timeline, and then afterwards have some extra support methods for creating clips from the timeline that can be used as their own instances or just separate animations to be interpolated together. Although a lot of that extra stuff would be handled by the skin models themselves. I suppose another way to do it would be to have a separate clip class, but we're not going to get into that stuff in this tutorial. Like I said, there's not going to be a whole lot of redundancy, so we're not going to worry about it too much. That's just something to think about in the future. So let's go to init and allocate some memory for the skin models. Under init3d, say hero equals new skin model, and we'll probably interpolate 3 for now. Actually, for the moment, we'll just load the 1 and test it out. So in load, I started by adding this SkinEffects is equal to new SkinEffects, passing in content, camera, and the skin effect that it needs to load. If we bring up Monogame Content Builder Editor here, we can right click on that and click Rebuild. And we just got some truncations, so that should be fine. Now we can say SkinModelLoader is equal to new SkinModelLoader, pass in content and GPU. And now that we have that, let's set the default options for it. Maybe we'll add 0.1 to pad out the animation loop to make it a little bit smoother. And we'll use default gray. I'll have to check the spelling of that in content. Yeah, it was default gray. So if one of the materials doesn't have texture, we'll use this default gray. And if the material has a diffuse color property, like red, then it'll become a red material. Next, we're loading the hero idle animation in that kid folder as kid_idle.fbx, and we actually do need the FBX here, specifying alternative directory of kid, so it'll know to search in there to find the images for the textures. I'm setting use debug texture to be true, although at the moment we don't have anything in our debug drawer to actually take advantage of that debug texture yet, but we can add that later. Our loading level preset is 3, which means we're using our own custom settings that we specified inside it. We're passing in the skin effects we want it to use, and we're rescaling it to 35% of its original size. So we need to make it a bit smaller. And we would do the same for walk. And for run, specifying walk and run here. I'm just going to comment these out because I don't have a walk or a run yet. And we don't have a separate actor class, so I'm just going to control everything in here for now. So I'll say matrix hero rotate and initially set him up to be facing the other direction because I decided I'd like him facing towards the camera at first. We'll make sure to update his world matrix in SkinEffects.world by assigning it here right after. Let's go down to update, and we kind of have this level init thing here. If we're going into a new area, we want to reset our character. So we begin animation 0, send in the starting game time so it knows how to start timing things. If you did have an option to go through the frames, i.e. using the arrow keys or something to go one frame at a time for debugging or whatever, you'd be changing the override anim frame time each time. So in this case, we'd want to make sure that we set that back to -1. That's the default, and we're not doing anything like that, so I can take that out. Now we're done our init, so I'll say init equals false. And if we load a new level and we want to reset things, we can set init to be true. So right after we update our camera, we may as well update our hero. For the moment, I'm just going to test updating the one animation, so I'll just say update for idle, pass in game time. If we go down to draw, under this set 3D states, we could draw our character like this, but in our case we'd like to set some specific material properties as we draw it to make it look a little bit better. So I'll comment that out, and we'll add a specialized routine here. Okay, so I added some code for that. I commented here normal way for this, specialized way is here. So I'm going to reference the hero idle and set that as my model, kid, and then I'm going to loop through the meshes in it and reference the current mesh here. If the mesh's opacity is less than 0.6, we'll skip this one because that's the reflective shine on the eyes, that's that outer shell of the eyes, and we'll render that down here instead. I'll set the diffuse color to white, converting it to a vector 4. Set the specular color, red 0.2, green 0.3, blue 0.05. This is up to you. This is a fairly transparent specular color, so not a whole lot of specularity. A specular power of 256, controlling that glossiness. For our world matrix, that's the position and orientation of the player, we'll multiply the hero rotation matrix by a translation matrix created from hero position. And as noted here, this has to be set before setDrawParams is called. If we peek the DrawMesh, you can see that setDrawParams is called right here. So in this case, we know that setDrawParams is going to be called just before draw user indexed primitives. And use specular material by default is false. We'll set that to true for the eyes though. Oh no wait, we're not going to use the material specular, we're using our own specular for everything. So it'll be false for all of this. So now we've drawn everything except for the shells for the eyes, that's that reflective shiny part. So I'm going to set this parameter, set shine amplify to 100, and we'll set it to 1 when we're finished. We're doing the exact same thing here, except this time I'm checking to see if the opacity is greater than or equal to 0.6, and if it is, then it's not the surfaces of the eye, so it's just going to skip it with that continue. We'll preserve the old alpha value as the SkinEffects.alpha, and we'll temporarily change it to 0.2 to make sure that it's nice and low so the shader knows what our intentions are. Also partly to make it that much more see-through. And we'll set that diffuse color of the material to blue, the specular color to 100% on white, more than 100%. 100% would be 111. And then we'll draw that current mesh using our own specular values. And we're not using the loaded mesh materials, just our own regular mesh material setup. Okay, now to look for some bugs and see if we can test this. Oh, back in our SkinModelLoader, we changed this to because we don't need a mesh index for going through all the meshes. So we'll take that 0 out of there and save it and build. Okay, let's see what happens when we run it. Okay, the normals look good. You can see the normal lighting effect fairly well inside the tail, actually, and a little bit in the fabric, and on the flowers and the shoes. And you can kind of see it in the eyes, although it's a little harder to tell. Yeah, you can see it at certain angles. Like right now you can tell. Especially along the rim of where the coloring of the eye starts. You can see the lighting value change as you turn. Now, since I flipped the Y direction of the camera, controls seem a little bit wonky. It might be because it's zoomed up so close right now. We may end up having to go into the camera control and make sure that everything's working right there. And the next things we'll need to do is export our kid walk and kid run. So it's the same sort of thing. I don't want to use the consolidated mesh versions with these because this one's not consolidated. And I did that to test this version. So I'd like to test all three of them working together. Once we have those in those folders, we'll just have to go to our update and also include here updates for walk and run. And then that way all those transforms are updated. The next thing to do would be to create a version of DrawMesh where we can reference a number of other animations as well as a desired interpolation value. And you can base this all off of the other tutorial videos that I made where we were interpolating between the walk, the idle, the walk, and the run. We'd pass in those other model references, and then for each one of those, we'd have to extract, using the same mesh index, a reference to each of those meshes. So we'd have a list of them. Chances are good it would only be 2 or 3. And then interpolate, for example, M1.shader matrices, M2.shader matrices, M3.shader matrices. So we'd need something right here to interpolate the shader matrices for each of those based on that in-between value. So what percentage between the two animations we want it blended. And it could be a 2-stage interpolation too, like we might have an interpolation between idle and walk, or walk and run, and then the second stage, it would interpolate between whatever that's doing and maybe a jump. So we could include something like that in here. And we could also choose to have certain animations set for the lower half of the body's meshes, and then maybe different animations set for the upper half of the body's meshes. If it's all a singular mesh, then it would just be for the bones. That gets a little bit more complicated to explain, but you'd have the upper bones doing something a bit different than the bottom bones by using a different set of animations from a different animation clip, if we're to do it that way, or just a different character animation in general. But I'd probably put that in a separate DrawMesh that's a little more specialized. And then we can pass our final blended shader matrices into bones. Chances are good we're safe. It's just using the idles node with animatrans here. It's probably just an identity matrix. But yeah, that's basically it. We're just trying to interpolate between the shader matrices of each character animation based on how much we want of each of the two animations. And regardless of which animation it's using, we can just leave this as kid, hero, idle for the basis for materials and texture setup and all that. That part's not really going to matter. The DrawMesh part is where it's going to decide how to construct the animations and show the final animated character. So that's where that would come into play. Then we just have to make sure we call the same new version of the DrawMesh down here. So for example, we might have a version or an overload of this where we'd also pass in a reference to the other animation that we want to blend to. And actually, we could set that up ahead of time. We could just send it a reference to the other shader matrices and the blend amount. So we could have some logic up here that would extract the shader matrices, the second shader matrices, based on whether we're blending between idle and walk or walk and run, and then deciding what the blend amount is based on the controller. I'm not going to do that in this tutorial, but I'm going to be working on my own game for a while, but I may come back to this later and eventually add those animation interpolations stuff that I talked about, as well as some soft shadow mapping, and then some very basic collision detection stuff. Well, hopefully that's useful. Hopefully you can make something out of this. Good luck!